Alright, let's talk about nuclear chemistry. Our story begins all the way back to the days of the alchemists, so before the 1600s. And as you may recall from one of our earlier lectures, the idea behind alchemy was that you could produce metals, certain metals, you could extract them from their ores and get those particular metals isolated. Metals like tin, copper, even iron, you could make, isolate, and purify. But the idea behind alchemy was that there was an elixir of life that resided within the ether, and the ether was this membrane, so to speak, that permeated throughout um, the atmosphere. It was invisible and imperceptible, but it was there, according to alchemists. And it was within this ether that you could find the elixir of life, which would allow you to basically transmutate an element into another, specifically transmutate a common metal like copper or tin into a noble metal like gold. So this was the whole idea behind alchemy. And not to say that all of alchemy was nonsense, but certain things that came from alchemy ultimately paved the road for what we now know as chemistry. But the ideas behind it were totally wrong. There is no ether and there is no elixir of life. Um, so unfortunately, they were just going after a fool's errand. But the interesting thing about it is that this idea of changing an element into another is actually not completely out of the question. Although, via the methods that the alchemists were trying to approach it, is actually not really possible. So, by the 1600s, when the scientific method gets established, Dalton comes up with his principles, the 5 principles, that basically tell you that the elements are made out of indivisible parts. Atoms of the same element have the same mass. Compounds are made out of atoms of different elements. Chemical reactions involve the reorganization of the atoms, and atoms cannot be created or destroyed. And I did mention in a previous lecture that actually 3 out of these 5 statements are technically wrong. Elements are actually made out of indivisible parts, elementary particles to be most exact. And granted, when you get down to that level, you lose the chemical property of what used to be an element, but you can break the element into smaller parts. Um, all atoms of the same element have the same mass. That we know already that that's not true because different elements have different isotopes and each isotope has a different mass, right? So that's definitely not true. Now the last one, the fact that atoms cannot be created or destroyed, this is a corollary of the conservation of mass, but it's actually incorrect because you can, via the processes of nuclear chemistry, um, change one element into another. And so in essence, you are kind of destroying some of those elements and creating other ones. And so the idea that alchemists had technically wasn't wrong. The way in which they were trying to approach it, however, was totally wrong. So we're going to touch upon this idea of changing the elements from one to another via the process of nuclear chemistry. And incidentally, this will bring us to the idea of relativity, because as it turns out, it is right at the nucleus of the atom that relativity and quantum mechanics meet. These two theories are very much incongruent with one another. They don't agree with each other, but in the atom is where you actually see the effects of relativity taking place. So it's kind of interesting that the theory that explains the natural aspect of the very large is actually present in the aspects of the very small, the atom. So yeah, the energy equals mc squared. Basically what tells you is that energy can actually be exchanged into mass or mass can be changed into energy. So the same way that we talked about heat being exchanged from one substance to another, here the energy, heat, can be used to make mass or mass can be used to produce energy. And so nuclear reactions actually are a source of vast amounts of energy, as you will see. Now historically too, um, nuclear chemistry didn't become a thing until the 1930s, 1940s, when most of the experiments got not only done but worked out. And one of the places where this happened was at Los Alamos National Lab in New Mexico, about 40 miles east of Santa Fe. So pretty much in Los Alamos Lab is where the Manhattan Project took place. And the Manhattan Project, for those of you who may not know, is the main task of producing the atomic bomb. Not for the sake of making the bomb, period, but it was a result of the fact that at the time World War II was taking place, and many scientists, including Einstein himself, which migrated to the United States as a result of the huge threat of the Nazi regime, appearing in Europe. Many of these scientists basically talked to the president, the U.S. president at the time, about the possible issues, not just issues, but the problems, right? The imminent problems that came with the Nazi regime, and that they had to get going on developing the atomic bomb because this was already being done in Europe, and this could be quite catastrophic, if the opposite the opposite regimes were to get a hold of it first. So the Manhattan Project was basically a secret project that was placed in New Mexico, kind of in the middle of nowhere, on purpose because he wanted to be secret. But here's where the atomic bomb was developed, and the ideas of Einstein, E equals mc squared, ultimately are manifested by this thing. And yes, this is a very destructive thing. It's not a bomb or an arsenal that you want to be using continuously, because this actually messes up the atmosphere of the earth. Not to mention the fact that you are contaminating the soil nearby with highly radioactive substances. But aside from the atomic bomb, you also have the nuclear reactors that do generate enough power that can actually provide energy, electricity, and heat to entire cities. There's, of course, problems associated with them. You might even recall what happened uh, to Fukushima in Japan with the tsunami. So there are issues, obviously, associated with nuclear power, and care must be taken to account for possible problems of that sort. All right, now all that being said, what we're going to be focusing almost entirely in this class will be balancing nuclear reactions. And it's a different way of looking at balancing. But as you'll probably find out and come to appreciate, in some ways it's perhaps easier than balancing chemical equations. All right, before we can do that, though, I do need to introduce nuclear notation for you guys. Um, Nuclear notation follows the same type of symbolism that we used before for isotopes. We're going to have the element present in here with its symbol, and on the bottom left corner we're going to have the atomic number of the element. On top, on the left side of the element, we'll have the mass number. So this is basically the same configuration that we've used for referring to isotopes. The atomic number represents the number of protons for the isotope. The number of neutrons is simply the subtraction of the mass number with the atomic number. And together, the number of protons and neutrons are the nucleus. So in essence, the mass number represents the number of nucleons that you have present in your element. And it's the changes that will be taking place in the nuclear reaction, the nucleus, that we do depict as nuclear reactions themselves. But this need not be completely allocated to elements. In fact, there are going to be some elementary particles that do play key roles in nuclear reactions, and we need to also address them with the same type of symbolism. So in this case, X will not only represent an element, but it could represent a particle. The particle could be an electron, it could be a neutron, it could be a neutrino. We'll be depicting each one of those in a second. And what typically will be allocated as the atomic number now represents the charge of the particle. And this goes hand in hand with the atomic number, because atomic number, after all, is the number of protons, so automatically you have the charge of that nucleus by looking at the atomic number. The mass number is still the mass number. We place the mass of the particle in here from the point of view of the mass of the proton or neutron. So one particle that we want to look at and talk about is known as the alpha particle. We have two protons associated with them and two neutrons, so the mass is 4. So this is helium-4. This is known as the alpha particle. I need you to remember it as such. Another one that I may use from time to time, and although probably I'll just use the element symbol H instead of lowercase p, is the proton. The proton is basically a hydrogen atom minus an electron, but it does have a +1 charge, and it has an an atomic mass of 1. Then we have the beta particle. The beta particle, simply stated, it's an electron. And the electron, we use lowercase e to represent it. The electron has a charge of -1, so on the lower left corner we have the -1 symbol. And since the electron is so much smaller and so much lighter than the protons, the mass number is basically regarded as being 0. The antiparticle of the electron, known as the positron, also will play a role in nuclear reactions. We either refer to it as a positron or beta plus, and the symbolism is pretty much the same one as the electron, except that the charge is positive as opposed to being negative. All right, then we have straight out light waves of high energy, specifically gamma rays, for which we use the Greek letter gamma. And gamma rays, which is simply light, do not have any charge, so the number on the bottom is 0, and they don't have any mass either, so the mass is also 0. So technically, you would only be concerned in using the gamma rays to account for the overall energy that needs to be constant. And then you have your neutrons. Neutrons are definitely going to play a role. They don't have a charge, they're neutral, so the number on the bottom is 0, but they do have an atomic mass of 1. And then we have the neutrinos, which, as you'll see in a little bit, we'll use to fully balance certain types of reactions. Much like the gamma rays, they don't have a mass and they don't have a charge, so they have zeros for everything. But the neutrino has also an antiparticle known as the antineutrino, and since the masses are 0 and the charges are 0, the way we want to differentiate it, at least on writing, is by having this bar on top. Now, you may ask the question, well, what's really the difference? The charges are the same, the masses are the same. How come they're not the same thing? And normally, you'd be correct in making that assessment. But the thing about the neutrino and the antineutrino is that they never appear in the very specific equation that or reaction that you're carrying out. A neutrino will always appear in the process of an electron capture reaction, for instance. An antineutrino, on the other hand, will appear in the process of beta emission. And you never see a swapping between the two or the other. And the way they ultimately react with other particles is what allows us to determine that yes, they are different from each other and they are separate from one another. Needless to say, we're not going to be looking at each one of those details in this lecture because this is meant to be more of an introduction and at that, a very soft introduction into the realm of nuclear chemistry. Alright, but now that we've talked about the historical and aspects and the nuclear notation, in the next video, what I'm going to begin doing is talking about the individual types of nuclear reactions. So with that being said, we'll stop right here and I'll see you in the next video.